Welcome to Brain Vision.
Hi everyone, so what we have is a pipe that has air going through it. The air is at an initial temperature of 300 Kelvin and an initial pressure of 100 kPa. There is a fan in this pipe that is given an input power of 1500 watts, and after passing through this fan, the air has a temperature of 80 degrees Celsius. And what we're asked to do is manipulate the exit velocity between 5 and 25 meters per second to see its effect on the mass flow rate, volume flow rate through this pipe. So the first thing we're going to do is just write down the properties of our gas. Since we're assuming that air is an ideal gas, we can say that our R value, or the gas constant, is 0.287 kilojoules per kilogram Kelvin. We can also say that the Cp value will be equal to 1.005 kilojoules per kilogram Kelvin. Next, we take the pipe as our system and as the control volume, and we can say that the energy coming in is going to be equal to the energy coming out. And this is because we're assuming that this is operating at steady state conditions. We can go ahead and break this down into its constituents by saying that energy in is equal to the m dot h1 plus the kinetic energy plus the work input, which is equal to m dot times the enthalpy plus the kinetic energy leaving. Now recall that we assume that the air is starting from rest, so the initial kinetic energy is just going to be equal to 0. Now what we can do is go ahead and just solve for work, and we see that work will be equal to m dot Cp T2 minus T1 plus V2 squared all over 2. And this, how we got this was just by manipulating terms and using the expression that enthalpy is equal to Cp times T. So now recall that we are actually solving for m dot. So solving this equation for m dot gives us that m dot is equal, w dot is going to be equal to w dot all over Cp times T2 minus T1 plus V2 squared over 2. Now recall that the problem statement asks us to vary the exit velocity, or V2, to see the effect on m dot. So this will be the first plot that we show. But before I show that plot, what we're going to do is see how changing the exit velocity affects volume flow rate as well. So how we do that is first by solving the exit specific volume. By using the ideal gas law, we can solve for V2 by saying that this is equal to R T2 over P2. Now these are all quantities that are given to us, and we see that the exit specific volume is 1.013 cubic meters per kilogram. We can use the specific volume to easily solve for the volume flow rate by saying that the volume flow rate at the exit is equal to m dot times V2. As you can see, this expression is dependent on m dot, which is dependent on the exit velocity. Therefore, this plot will also show some kind of relationship between exit velocity and volume flow rate, which will be the second graph that I show. So this graph here is the graph of exit velocity, which is shown on the x-axis, and m dot, which is shown on the y-axis. As you can see, as our exit velocity increases, the m dot decreases in a very non-dramatic way. And the reason I say that is because if you look at the scale on our m dot, the scale is extremely small, while the exit velocity increases very drastically. Similarly, we see that in the v dot as well. We have exit velocity on our x-axis and v dot on our y-axis. Initially, it seems that as the exit velocity increases, our v dot drastically decreases. However, looking at the scale and recognizing that the scale is very small, we see that there is some effect, but the effect is not as significant as it appears.